All right. So now we're going to apply the new learned technique of implicit differentiation to do things that are listed under section 3.7. All right. Let y be the nth root of x, which you can write as nth radical of x, or you can simply write this as x to the 1 over n. Right. Now we already did this for x to the 1/3, because then the inverse function of the third root is, x cubed, right? And so we saw one specific example, and it turned out that you can still use the power rule. The answer was you move this exponent to the front and then subtract 1 to create your new exponent. That worked out. Let's make sure that this is still the case. But now we can use not the inverse function theorem, but the implicit differentiation. Now, why is that? Okay, first I'm going to square, or not, I'm going to take the nth power of both. Okay, so y to the n is equal to x. Now this means the same thing, right? Assuming that this makes sense. So for instance, if n is even, then x has to be non-negative and so on. But if this is true, then y to the nth power is x. Okay. Now we do implicit differentiation. Implicit differentiation. Or you can say, take the derivative using implicit differentiation. Implicitly differentiate both sides. What do you get? N, remember n is an integer here, and then y to the n minus 1 is equal to 1. Oh, sorry. I said, the whole idea of implicit differentiation is to do this and then multiply that by the derivative of the inside function, which is y. So you have to have y prime here. And then x just becomes 1, right? Now, y prime is easily calculated, computed, okay? Because all you have to do is to divide both sides by n times y to the negative 1. Now, you can write this as 1 over n, and then y to the what? Well, it's minus n minus 1, right? And so what is that? That's 1 over n, and then y to the, and you can distribute the negative sign. It's 1 minus n. Okay, well, that's good, but what is y? Well, y is clearly written right here. So let's replace this y with x to the 1 over n, and then you take this to the 1 minus nth power. Okay, it gets a little complicated, but remember how these exponents work. If you have an exponent to an exponent, you multiply these two exponents. So it becomes 1 over n divided by n. Hang on just a second, because we will find the answer here. The answer is it's 1 over n minus 1. That's the new exponent, okay? Which, by the way, if you look at this, is exactly what we would have expected. You take that exponent of the original function y, you move it to the front as the coefficient, and you subtract 1 from the original exponent in order to come up with your new exponent. All right, cool. All right, this one is 1 minus the original exponent, right? Wow, this is good. So let me give you an example. And then I will do something else that is just an expansion of this before I state the extended version of the power rule. All right, so d dx of the square root of x, what do you think this is? It's x to the 1/2 power. So all you have to do is to move that 1/2 to the front, and then x to the new power, which is 1 less than 1/2. That's negative 1/2. Okay, you can write it. You can write this as your answer for your derivative, or if you want, you can of course write it this way as well. All right. So what is d dx of x to the 1/17? This is the 17th root of x. Why would anybody want to take the derivative of the 17th root of x? I have no idea. But if somebody did want to do that, this is how you would solve that. It's 1/17 times x to the 1/17 minus 1, which is negative 16/17. All right. Or you can write this as this way. All right, so these are as before. It's very nice that the power rule extends to these rational functions or radical functions. All right, now let's try to do something a little more than that. All right, so instead of just having 1 over n, what happens if you have n over m, m over n? So here, the exponent can be, I should say, the exponent can be any rational functions, right? Rational numbers. And what is a rational number? Rational number is m over n, where m and n are integers. And of course, n is not equal to 0 because you don't want to have the 0 denominator. So what we are about to do is to find some rule of differentiation where you have x to some power, where the power could be any rational number. Now, you know what a rational number is. In terms of a decimal number, it is either a terminating decimal or repeating decimal. All right, so for instance, 1/3 is 0.33333 and so on. So what happens, like when you have x to the 0.714211103? Okay, that's a terminating function, right? I mean, terminating decimal. So once you find the answer to this question, what the derivative is, then you should be able to calculate the derivative of something like that, because this is a rational function. This is, whatever this number is divided by some power of 10. All right, let's go ahead and do this. How do I do that? Well, that's the question. Okay, what is y prime? The first thing you should do is to write this as x to the 1 over n raised to the mth power, right? Then you can simply take the derivative. We know the derivative of the inside function, and m is an integer, so we can use the simple power rule we learned first. It's m times x to the 1 over n, and then m minus 1 times the derivative of the inside function. Remember the chain rule. So this multiplied by the derivative of the inside, which is 1 over n, x to the 1 over n minus 1. So somehow, if you can simplify this, we will find the answer to this. We can do that. All right. So the first easy part is you have m and 1 over m. Let's combine these. So you get m over n. Now we have to worry about the exponent of x. So you have that, which is what? M minus 1 times n. Okay. And then you also have x to the whatever this is. All right. So this can be written as 1 minus n over n. You see that? All right. How do you multiply x to something times x to something? Well, that's, x to the a times x to the b is x to the sum, right? So you have to add this and this together. Well, fortunately, we have the common denominator. How nice. M minus 1 plus 1 minus n is the new exponent. You can cancel the ones. And so this eventually comes to be x to the m minus n over n. What is that? Okay, it's m over n times x to the m over n minus n over n, which is 1. Okay, now does it look familiar? Well, look at it. The new exponent, well, first of all, the original exponent has become the coefficient in front as before in the power rule, the first power rule you learned. And then the new exponent is the original exponent minus 1. Okay, that's awesome, right? Because that power rule you learned first, it still applies. So at this point, let's go ahead and write what we have discovered, right? So extended, I should say, yet more extended power rule. See, the thing is, the power rule began with this exponent being in a positive integer. And then we extended it to include the negative integer exponent. And now we are going to include all rational exponents. And this one says the derivative of x to the any rational power is going to be that rational number as a coefficient times x to the mn minus 1. All right. Or you can say d dx of x to the r is r times x to the r minus 1 for any rational r. Cool. Oh, by the way, to say r is rational, sometimes you see this in the book. This subscript, or not subscript, this boldface Q, or the math font Q, represents a set of all rational numbers. So in other words, an integer over an integer where the denominator is not equal to 0. Okay, so that is, and again, this is, if I didn't tell you this, you may have just guessed that the power rule applies to all rational number exponents. But here is the proof that we just saw using implicit differentiation. Okay, let's do one example. And then we move into something even more fascinating. All right, so find the equation of the tangent line. Now, we haven't actually done a lot of these questions, equations of a tangent line, because this is assuming that you know how to write the equation of a line. Okay. Now you have, the point slope formula, which is what students are most familiar with, but you should also know the point slope form. Sorry, most people are familiar with the point intercept formula. Right? Y-intercept is given, mx plus b. That's what most people are familiar with. But there's another one that's, once you are given a point on the line, x1, y1, and the slope m is given, then the equation of the line is y minus y1 is equal to m times x minus x1. This is not something that many students are familiar with. If you are competent with this, that's great. If not, you may as well learn this because we will be using this quite a bit. This is called the point slope form of the equation of the line, right? All right, so let's say y is equal to x to the 2/5. Okay. Now, remember, this is the same thing as x to the 0.4th power. 0.4th? Yeah, 0.4 power, right? Because 2/5 is actually 0.4. But this is probably a better way to indicate that this is the 5th root of x squared. That's one way to think about this. Now, you probably can't just picture the graph of this function. I mean, I certainly couldn't until I graphed it using my graphing calculator. But I mean, you have certain things right? So the graph of this function is actually going to be like this, and then comes up like this. There's a sharp corner, right, where the derivative becomes infinite. And I have to give you a point. Okay? And the point is 1, 1. Okay, when x is equal to 1, y is equal to 1. So this is the point. My tangent line is going to look, something like this. All right, and that's my tangent line. Try to find not only the slope of the tangent line, but let's try to come up with the equation of the tangent line, L, right? So find the equation of this line, L, which is tangent to the function x to the 2/5 power at 0.11. That is the formal statement of this problem. All right, so how do you do that? By the way, here, this is 1 and this is 1. 1 is given as a point on the graph where the tangent line takes place, and we are to find the slope of this first. Okay, so the slope, y prime. This is really easy. Take that exponent times x to the new exponent, which is 2/5 minus 1, right? So that would be negative 3/5. Evaluate this at 1, and you get 2/5. No problem, right? Because I mean, the fifth root of 1 is 1, and then 1 to the negative third is also going to be 1. So that's no problem. What's the answer here? Y minus 1 is equal to 2/5 times, remember I'm using this point slope formula, y minus the y value of the point is equal to the slope times x minus the x value of the point, which is that. Okay, so this is a fine answer. If I ask you to find an equation of the line L, this is okay. If you are like most other people in the math world who insist on having the y-intercept form of the equation, you can certainly do that. This is 2/5 x minus 2/5. So y is 2/5 x plus 3/5. And now you know that this y-intercept has to be 3/5. But again, you don't, this is okay, but so is this. All right. Okay, now when we come back to the last segment of this video for section 3.8, we are going to face the new challenge of, and it's not going to be hard, okay, but it's going to be about inverse trig functions. We are going to differentiate inverse trig functions using some geometry and implicit differentiation. That will be great, okay? I promise it'll be really exciting. All right,